So we're trying to find the probability for the situation where there are 3 green marbles, 7 red marbles, and 5 white marbles in a bag. That is a total of 15 marbles. Okay, so number 14 asks for the probability that the chosen marble is white. So there are 5 white marbles out of a total of 15 possible marbles, which equals 1/3. So the probability is 1/3. Remember that here the important thing to remember is we want to do the number of favorable outcomes divided by the number of total outcomes, or the number of total outcomes in the sample space. So in this case, the favorable outcomes means the chosen marble is white. So there's 5 of those, and there are 15 total outcomes. Okay, this assumes that all the outcomes are equally likely, which in this case it is, because you're just picking marbles randomly out of a bag. Okay, so number 15 asks, the chosen marble is red or white. Okay, so the number of marbles that are red or white is 7 plus 5, so that would be 12. Okay, so we have 12 red or white marbles over 15 total marbles, so that equals 4 divided by 5. So 4/5 or 80%. Okay, number 16. 2 integers from 1 to 8 are randomly selected. The same number can be chosen both times. What is the probability that both numbers are greater than 2? Okay, so you have random numbers between 1 and 8. All right, so the probability that a number is greater than 2, well, how many different ways can we do that? Well, the number has to be 3, 4, 5, 6, 7, or 8. 3, 4, 5, 6, 7, or 8. So there are 6 possible outcomes out of a total of 8. Okay, which is equal to 6 over 8 or 3 over 4. So that's the probability that one of the 2 randomly chosen numbers is greater than 2. Okay, but we don't want just one of them to be greater than 2. We want both of them to be greater than 2. Okay, so here we have the probability for the first one, the probability for the second one, and they're both 3 over 4. So what do we want to do here? Do we want to add them? We'll just think about that. If we add them, we would get 1.5, which is not even a possible probability. Okay, we don't want to add them. We want to multiply these 2 probabilities. Okay, and the reason we do that is because we're saying the first 3/4 represents the probability that the first number chosen is greater than 2. Okay, and of those, right, so that means 75% of the time the first number will be greater than 2. And of those 75%, right, 75% of that will have the second number also greater than 2. So we want 75% of 75%, or 3/4 of 3/4, which is 3/4 times 3/4. So the answer is 9 over 16. Okay? All right, so that was number 16, 9 over 16. Okay, so number 17 says, the coach randomly selects 3 swimmers from a team of 8 to swim in a heat. What is the probability that she will choose the 3 strongest swimmers? Okay, so we have 5, 6, 7, 8 different swimmers, and let's just make 3 of them the fastest ones. Okay, so I'll just put them in a different color. Okay, so these 3 are the 3 fastest swimmers. Okay, so one way we can think about this is that for the first one chosen by the coach, the first swimmer, what is the probability that the first chosen swimmer is one of the 3 blue fast swimmers? Okay, since there are 3 of those out of a total of 8, right, the probability would be 3 over 8. Okay, so now this one has been chosen, okay? So now we just look at the remaining ones. Out of the remaining now 7 swimmers, what is the probability that the coach chooses one of the 2 blue fast swimmers? Well, there's 2 blue ones out of 7 remaining. So we'd have 2 over 7. Okay, so we have another one gone. Okay, and then lastly, we have 6 remaining swimmers and only one of them is a strong swimmer. Okay, so the probability of choosing this one fast swimmer randomly would be 1 out of 6. Okay, now what do we do with these numbers? Do we add them? No, we multiply them. Okay, the reason we multiply them is because these events all have to happen sort of on top of each other or in conjunction, right? So not only do you need to have this event that has a probability of 3/8, but that needs to happen, and this event separately that has a probability of 2/7 needs to occur, and then this another event which has a probability of 1/6 has to occur. So all of these have to occur. Okay, at any step you could just go off and get an unfavorable outcome, but we have to, each of these represents the probability of the favorable outcome at that step. Okay, so we have to multiply all of these numbers. So we end up getting, well, you see there's a 3 and a 2 on the top and a 6 on the bottom, so those will just cancel out. So this equals 1/8 times 7, or 1/56. Okay, another way to think about that is a couple different ways. So what is the number of ways that the coach can choose 3 swimmers from a group of 8? The number of ways to choose 3 swimmers from a group of 8 is 8C3, okay? And there's only one way that you can pick the three strongest swimmers, right? Either you pick the 3 strongest swimmers or you don't, okay? So there's only one way to do that. Again, we're doing combinations here. We're saying order doesn't matter, okay? So there's one correct way to pick the 3 strongest swimmers out of a total of 8C3 different ways to choose 3 swimmers from a group of 8. Okay, so that's going to be 1 over, and 8C3, that's going to be equal to 8 times 7 times 6 over 3 times 2 times 1. So we're going to end up getting 1 over, notice that the 6 and the 3 and the 2 will cancel out. So we'll get, again, 1/8 times 7, which is 1/56. So again, we get the same answer. Bye. Okay, number 18. There are 7 books numbered 1 through 7 on the summer reading list. Peter randomly chooses 2 books. What is the probability that Peter chooses books numbered 1 and 2? Okay, so a couple different ways we could think about this. So again, going off the last example, we can have 7 books, 1, 2, 3, 4, 5, 6, 7, and we're going to have 2 of them that we're just going to decide are special. Okay, they're books numbers 1 and 2. Okay, so out of our 7 books, 2 of them are numbers 1 and 2. Now, here it's saying that what is the probability that Peter chooses those 2 books? So even though they're numbered 1 and 2, the order here doesn't actually matter. The order that Peter picks them in doesn't matter. He could pick 1 and then 2, or 2 and then 1, and that's not important. Okay, so just keep that in mind. Okay, so what is the probability that he will pick one of these 2 books on his first pick? So on his first pick, there's 7 books to choose from, and there are 2 desirable or favorable outcomes. Okay, so it's going to be 2 out of 7. And then on his second, it will be 1 out of 6, okay, after this one is gone. Okay, so we're going to have 2 over 7 times 1 over 6, which will equal 2 over 42, which equals 1 over 21. Okay, so is there another way we can think about this? Yes, there is. Okay, so the number of ways to pick 2 books from a group of 7 would be given by 7C2. Okay, that is the number of ways to pick 2 books from a group of 7 books. Okay, that's your total possible outcomes, and that is equal to 7 times 6 over 2 times 1, which equals 21. Okay, and only one of those 21 ways is going to give you books 1 and 2. Again, we're using combinations here, so order doesn't matter. It would count books 1 and 2 as the same as books 2 and 1. Okay, so out of your 21 different ways to choose 2 books, only one of those is going to correspond to picking books 1 and 2. Okay, so there are 21 ways, and only one of them is going to give us the favorable outcome, so our answer is 1 over 21. Again, get the same answer using a slightly different approach. Okay, games. In a game of corn toss, players throw corn-filled bags at a hole. Okay, so let's calculate the area of the entire platform. Okay, so the area of the platform is 4 feet by 2 feet, which is 8 square feet, okay? And the area of the hole, right, 6-inch diameter, which means the radius equals 3 inches, okay? Now, it so happens that 3 inches equals what proportion of a foot? Well, 3 inches is a quarter of a foot, so it's 0.25 feet, or 1/4 of a foot, okay? So that's our radius. And so the area of the hole equals pi times radius squared, which equals pi times 1/4 squared. We're just going to do everything in feet here to have the same units, okay? So it's going to equal pi times 1/16. Okay, so now we want to compare the ratio of the area of the hole to the area of the whole board, okay? So we calculated the area of the board before. It was 8 square feet. So we're going to have, 1/16 pi over 8 feet. Okay. So to get a rough idea of what that would be, right? That's going to be equal to pi over 16 times 8. Okay, so 16 times 8 is equal to 128. So we're going to get pi over 128, which is roughly, what is that going to be? A little under 3, 2 point something percent. So yeah, I mean, it's pretty unlikely if you're throwing randomly. Of course, this assumes that you're throwing randomly, which is obviously not necessarily true. Okay, so you have probably better than 2% chance of getting it. Okay, you were dealt 3 cards randomly from a 52 card deck. What is the probability that they are all face cards? Okay, so we have 3 cards randomly from a 52 card deck. How many ways are there to choose 3 cards from a 52 card deck? Okay, so the way to do that is, it doesn't say anything about the order, you're just drawing 3 cards, right? So you have 52 cards, and you are choosing 3. Okay, so 52C3, a combination of 3 cards from a deck of 52. Okay, the probability that they are all face cards. Okay, so here's the tricky part, right? We have the number of total possibilities, but what is the number of favorable outcomes, right? Well, we just have to calculate every single way that you could get 3 face cards, okay? Well, how many face cards are there? Well, there are 12 face cards. So how many ways can we arrange 12 face cards? Or how many ways can we pick a set of 3 from 12? Well, it's 12C3. Okay, so our answer would be 12C3 divided by 52C3. Okay, so 12C3 represents number of ways to pick 3 face cards. And this represents, I'm just going to copy this, but change one important thing, which is that this is not the number of face cards, but just the number of way to pick 3 cards in general from a deck. Okay, so let's see what this would be. 12C3 over 52C3. Okay, so 12C3 is 12 times 11 times 10 over 3 times 2 times 1 divided by 52 times 51 times 50 over 3 times 2 times 1. Okay, so notice that we have a 3 times 2 times 1 in the denominator in both the top and the bottom, so those actually cancel out. So this just equals 12 times 11 times 10 over 52 times 51 times 50. Okay, and there are some other simplifications that we could do, right? But for now, you can just plug that into your calculator to get the decimal equivalent. Okay, but that would be the probability that your 3 randomly chosen cards are all face cards. Okay, what is the probability that all 3 cards are aces? Okay, here it's a very similar setup. Denominator will be, again, 52C3, because that's the number of ways that you can choose 3 cards. But how many ways can you choose 3 aces? Well, there's actually only 4 aces in the whole deck, right? So the number of ways to choose 3 aces is just 4C3, okay? And guess what 4C3 is? 4C3 is equal to 4 times 3 times 2 over 3 times 2 times 1. Well, that just equals 4. There are only 4 different ways to choose 3 cards from a set of 4. The reason is, if you choose a set of 3, that's the same as choosing which one you're not going to choose, which one you're not including, right? So you can not include the ace of spades. That gives you your 3 other cards. You can not include the ace of hearts. You can not include the ace of spades, and so on. So there's only 4 different ways that you can choose a group of 3. Okay, so our total probability would just be 4 over 52 times 51 times 50 over 3 times 2 times 1. Okay, so again, this is going to be a pretty small probability. Okay, a family has 5 kids. What is the probability that they have 1 girl and 4 boys? Okay, so think about how many ways you could have 5 kids. This is very similar to the flipping a coin discussion. But if you're having kids, assuming the gender is random, since there are 2 options, boy and girl, and you have 5 kids, there are 2 to the 5 different options. Now, keep in mind, this is not going to be one of those 5p something examples on the bottom, because it's more like flipping a coin. Each child can be either a boy or a girl, and is not really affected by the previous children. It's not like it's going to be a 5 times 4 times 3 times 2 times 1 kind of scenario. It's just each child can be boy or girl, 2 options times 2 options times 2 options times 2 options times 2 options. So 2 to the power of 5, which equals 32. So that's going to be our denominator. That's the total number of different ways you can get 5 kids. Okay, and the number of ways that you can have 1 girl out of 5 kids is just 5C1. Okay, 5C1 means you have a group of 5 and you want to choose 1. Okay, so we saw examples in class where you have a family of 5 playing Mafia. How many ways could you choose 1 Mafia? Well, it would just be 5C1. Okay, which is the same as, actually it's the same as 5P1. Okay, because you're only choosing 1 person. Okay, so the answer to that, 5C1 equals just 5. Okay, which means your girl, that makes sense because your girl could just be your oldest, the girl could be the 2nd oldest, the girl could be the 3rd oldest, the 4th oldest, or the 5th oldest. There are really just 5 options. Okay, so you have 5 different ways that you could have 1 girl and 4 boys. So 5 divided by 32. Okay, so 5 divided by 32, that's a pretty small number. What is that? About like 15-16%, something like that. So not huge, but not crazy unlikely either. Okay, so let's compare that with the probability of having 2 girls and 3 boys. Okay, so the only thing that changes here is we have a 5C2 in the numerator instead of a 5C1. Okay, and the denominator will still be 2 to the 5. Okay, so that will equal 5 times 4 over 2 times 1 on the top divided by 32. So that will equal 10 on the top divided by 32. Okay, so this is twice as likely. Okay, there are twice as many ways that this can happen, that you can have 2 girls and 3 boys. So the probability is actually twice as great as the previous example. It's almost a third, 33, more than 33%, or a little under 33% probability that you will have 2 girls and 3 boys. And obviously it's symmetrical, right? You could replace girls and boys, it would be the same. So the probability that you get 2 boys and 3 girls would be exactly the same, 10 over 32.